Everyone. Thanks for watching. My name is Jason, and I'll be telling you about our work on learning Ising models beyond independence and bounded width. And this is joint work with Elkan and Mosel. So to introduce Ising models, these are just high-dimensional distributions over spin configurations on plus minus 1 to the n. And the defining feature is that they're going to kind of be governed by pairwise interactions. And so Ising models are like a foundational model across a wide variety of domains like probability theory, statistics, computer science, economics, and engineering broadly. And they're very simple models to write out, but they're very mathematically rich. So in particular, they exhibit all sorts of interesting phenomena like spatial correlations across sites. They exhibit phase transitions when you think about scaling the degree of the interactions up and down. And they have very interesting dynamical behavior. For instance, if you consider like Markov chains on these Ising models that are supposed to sample from the stationary measure, there's all sorts of interesting phenomena like fast mixing or torpid mixing. So formally, the Ising model is defined as follows. Given a symmetric matrix A and external fields H in Rn, the Ising model mu, which is going to be parameterized by A and H on plus minus 1 to the n, is going to be given as follows. The distribution is going to be such that the probability of a spin configuration X is going to be proportional to e to the 1/2 of the quadratic form of X and A plus H transpose X. And so to make this a distribution, you just divide by what's called the partition function, which is going to be the sum of these e to these terms. So for instance, the matrix A might be kind of 0 except for kind of graph edges and kind of like a lattice structure, for instance, like this picture here. Or for instance, A might have non-zero entries everywhere. So you can think of it as kind of being a complete graph with non-trivial interactions between all sites. So some common examples of this are kind of like the most basic one in some senses, what's called the Curie-Weiss model, where all the interactions are just going to be proportional to 1 between any two sites. A more interesting model, which we'll talk about in a bit, is what's called the Sherrington-Kirkpatrick model. So this is going to be defined as follows. There's going to be some inverse temperature beta, which you should think of as a constant. And the interaction matrix A is just going to be beta times G, where G is going to be a GOE matrix. So this is a matrix with independent entries, which are going to be filled with IID Gaussians with variance 1 over n, and it's going to be symmetric. And then you might have Ising models that kind of have this sort of interesting random interactions between entries, but you might kind of have like a lattice structure. So this would be kind of this model over here. So in this talk, we're going to be talking about the problem of what's called parameter learning of Ising models. So namely, what's going to happen is we're going to get some sort of observations from this measure mu AH, and our goal is going to be to output estimates A hat and H hat, which should be close to A and H in some sense. So the questions we're going to be considering are as follows. The first is, what kinds of observations do you need to learn this measure, or at least the parameters? And the second is, what assumptions do we actually need on A and H to efficiently learn, given whatever these observations are? So these are going to be the two questions that are going to kind of guide the rest of this talk. So just for some history, this is a very well-studied problem in the statistics and computer science literature, especially in the last decade. So the first efficient algorithm for the somewhat weaker problem that's called structure learning is by Bressler, and it works on bounded degree graphs. And since then, there's kind of been a number of algorithmic frameworks, a bit more kind of optimization oriented, that solve this kind of harder problem of parameter recovering from samples. So for instance, things like multiplicative weights, something called interaction screening, and something we'll talk about a bit more, which is logistic regression. All of these are kind of different algorithmic frameworks that solve this parameter recovery problem. And then there's kind of a wide variety of other works where they are kind of variations on this learning problem. But for us, we're going to be kind of focused on this original fundamental learning problem of parameter recovery from samples. So to state the kind of state-of-the-art guarantees, we need a little bit of notation. So we're going to define the L1 width of the model parameterized by A and H. We're going to call it lambda. And lambda is just going to be the maximum L1 norm of a row of the matrix plus the magnitude of the corresponding field entry. So the state of the art guarantees are going to be given as follows. Suppose we're given IID samples x1 through xp from the measure mu AH. Then these algorithms from these prior works will efficiently estimate A and H up to some additive epsilon error with high probability, so long as the number of samples P is going to be at least something like e to the lambda with some constant C times log n times poly 1 over epsilon, which won't be too important for us. Kind of the key points, though, are that this dependence on n and this L1 with lambda are actually known to be tight. So in some sense, you might be asking, okay, what else is there to do? We have kind of good algorithms that are efficient and kind of have basically optimal sample complexity given these information theoretic lower bounds. But one thing you can do is let's revisit the assumptions for a moment. So the first question we had asked was, what kinds of data and samples or observations do you need to actually learn the measure or the parameters? And the first thing we can ask is, are IID samples a reasonable assumption? And it's a nice assumption, at least for mathematical modeling, because it's very analytically nice. But the issue is like the assumption that you get IID samples from the measure can often be practically infeasible, if not computationally impossible. So it's known, for instance, that things like rapid mixing are often false, slow, or hard to prove. And in particular, if you think about your data being coming from some sort of natural or physical process, like a Markov chain, it'll be the case that it's unreasonable to expect to get IID samples from the measure if kind of these physical processes can't generate samples efficiently from the stationary measure. So in fact, in some applications, you might actually believe it's more natural to observe this evolution of the Markov chain directly and not be getting these IID samples from mu AH. So for instance, you might think of like coordination games on networks or things like some sort of physical particle system that's out of equilibrium, and there's some Markov chain that takes it closer to stationarity, but perhaps not very fast. So the second question we had was, what assumptions on A and H are required to efficiently learn? So the results I told you before corresponded to this bounded L1 width. But one thing we can ask is, what does this even mean physically, if anything at all? So this L1 width is superficially related to what's called this de Bruijn condition for fast mixing. Namely, if you have an Ising model where lambda is strictly less than 1, then it's known that, for instance, if you have like Glauber dynamics, which is a popular Markov chain for sampling, it'll rapidly mix towards the stationary measure. The issue, though, is there's some kind of tenuous connection, though, because the de Bruijn condition has a well-known phase transition at lambda equals 1. Namely, there are Ising models where as soon as you get past lambda equals 1 in terms of the L1 width, the de Bruijn condition will fail and the model won't rapidly mix anymore. But on the other hand, these IID learning guarantees were smooth in this lambda parameter. Namely, they were like e to the something times lambda. So even though the learning guarantees are smooth, something really does change in terms of the mixing properties. So in some sense, the lambda, the kind of connection between those two things isn't so clear. Even worse, there's a lot of interesting models where this L1 width is not going to be bounded at all, and the learning guarantees are going to be very weak. So for instance, in the Sherrington-Kirkpatrick model that I mentioned before, the lambda will be something like square root n because you're going to have like a vector of Gaussian entries and that'll concentrate really well around square root n. The issue is these learning guarantees generically will tell you that you need something like e to the square root n samples to learn it. And that's way worse than you should expect to be able to do, and in particular is not efficient at all. So taken in tandem, these two kind of observations suggest that this L1 width parameter, while it led to kind of nice and tight algorithmic guarantees in general, are not always the best way to parameterize the sample complexity of your problem. So our results are going to be about kind of going beyond these assumptions. And so our main results are going to say basically an existing method for Ising parameter recovery, namely logistic regression, can succeed well beyond these IID and bounded width settings. So in particular, if we use this vanilla logistic regression of this work of Wu, Sangavi, and Demakis, and you do it for using correlated samples, x1, x2, so on, generated by like any nice Markov chain, it'll still efficiently recover the parameters with barely any degradation in sample complexity compared to the IID setting. Moreover, when you go back to the IID setting, but you go beyond this L1 bounded width setting, logistic regression will provably succeed anytime the model is what we'll call high temperature, and this will actually strictly generalize this bounded L1 width setting. And a kind of nice fact is that there's no algorithmic modification required at all for any of this. It's really just kind of in the analysis and the subsequent sample complexity for this to work. So let me just give a very high level of what this logistic regression approach is. So the logistic loss is defined as log 1 plus e to the minus z. And so what you do is, suppose you know that each row of A lies in some known convex set C. So for instance, like the L1 or L2 ball or something like this. Then what you do is for a given site I, you want to recover the row AI. So what you do is, given some samples x1 through xp in plus minus 1 to the n, you'll solve the following problem. Namely, you're going to take the sum of the logistic losses with this argument, which will basically be the spin at site I on the kth sample. And then this term here is going to be kind of the field that's acting on that site, given the values of the other coordinates, and as if the true interactions were W. And so what you'll do is you'll just minimize the coefficients over this convex set. So what you do is you just kind of localize the observations. You look at person n. You know that person's n's distribution should have the right conditional measure given the samples outside it. And so you just solve this logistic regression problem and you return the output. So our first main result is that suppose you observe a nice Markov chain, in particular the trajectory of it. And the guarantee you have on the Markov chain is this, that at each time, some subset of variables updates according to the conditional law of the measure, given the variables that did not update. If it's the case that on this trajectory, each node updates at least this many times, given in this quantity here, where again, we're kind of parameterizing by the L1 width, then it'll be the case that this node-wise logistic regression I put on the previous slide will return an epsilon additive estimate of A with high probability, just like the IID case. And this sample complexity here is actually the same as you'll get in the IID case. We just have some extra logarithmic factors in the quantities that appear here. So in other words, basically, even though we have now very correlated data, the node-wise logistic regression will still succeed essentially with the same sample complexity as in the IID case. So I wrote this thing nice here, but basically it'll work for any nice Markov chain that you would encounter in practice, like Glauber dynamics or block dynamics, or even kind of round robin updates. So each site kind of updates one at a time. And this will hold for any starting configuration and without any guarantees on the mixing or things like this. So the only prior work on this problem was by Bressler, Gamarnik, and Shaw, and they gave kind of a specialized algorithm that solved the weaker problem of structure learning from Glauber dynamics on bounded degree graphs. So this result kind of improves on this in a couple different ways. One, I no longer need bounded degree, and it's the same algorithm as in the IID setting. It solves the parameter learning problem, and also it works for any nice Markov chain, including Glauber dynamics as a special case. So for high temperature Ising models to state the result, I need a little bit of notation. So given the symmetric convex set C, which is going to be kind of the set we know our Ising models rows belong to, you'll define the C operator norm on PSD matrices by just taking the biggest quadratic form over vectors in the convex set C and then just taking the square root. So for instance, if C is the L2 ball, this just directly generalizes kind of the normal spectral operator norm. So our second kind of main result informally stated is, suppose again that we know that A is such that all the rows lie in C. If I have this C operator norm on the covariance matrix of the model, and if the model has no external field, if I have such a bound on the covariance matrix, then logistic regression will succeed in learning A to epsilon error with high probability given independent IID samples from the measure. And the number of samples you need is just going to depend in a reasonable way on this operator norm bound, the Rademacher complexity of the class, and just 1 over epsilon, like poly 1 over epsilon. So the key point is, so long as L is something like at most logarithmic in N, and C is not too big, you're going to recover efficient learnability under this condition. And in particular, this recovers these prior L1 guarantees. If you just take the set C to be the L1 ball, because if you just work out what this is, because the spins are in plus minus one, you can apply Holder's inequality and kind of get this bound easily. But this result will kind of apply in more general settings, as I'll describe on the next slide. So in particular, this result has applications for this problem called spin glass inversion, which is the problem of learning the parameters of this SK model. So the result can be stated as follows. For any inverse temperature beta strictly less than 1, it'll hold with high probability over the realization of the random interaction matrix G, such that given poly n 1 over epsilon samples from the measure, logistic regression will output an epsilon additive approximation with high probability over the samples. So this result is interesting because beta strictly less than 1 is actually what's known to be the entire high temperature regime for the Sherrington-Kirkpatrick model at the level of things like free energy and replica symmetry. The only prior result to my knowledge on this problem was by Anari et al. And they show that you can do a weaker notion of learning called distribution learning for any beta less than a quarter. And the way that their result works is by reducing to a very difficult analytical condition called approximate tensorization of entropy, which implies, among other things, like modified log Sobolev inequalities and rapid mixing. But these things are not known beyond beta less than a quarter, or maybe slightly above this. So in particular, our result works by kind of reducing to weaker known properties of the measure, namely these covariance bounds. I want to mention also that our guarantee works kind of beyond the zero external field case. It can also handle kind of Gaussian external fields in the provable high temperature regime. And kind of these results kind of apply in other sampling models like what are called M regime samples and adversarial dynamics, but I won't talk about that in this talk. So let me just give a couple of the key ideas underlying these two results, this one from dynamics and this result for kind of high temperature Ising models in the sense of these covariance matrices. So one thing you need for logistic regression to work in all these applications is you require that these empirical logistic losses, the ones you're optimizing, should approximate certain population logistic losses. And what those are will kind of depend on if you're working from dynamics or from IID data. The issue, though, is the typical way to do this is using kind of standard techniques like bounded difference inequalities or Rademacher complexities. And this will just fail when you have temporally correlated data. So for us, we get around this by using kind of a more general theory called sequential Rademacher complexity as introduced by Rockland, Sridharan, and Tiwari. In either case, we'll still need to establish that even if you have this uniform convergence, things still work in the analysis. And it turns out from prior work, you can kind of do this so long as you can establish what I'll call variance lower bounds. So namely, what you need is when you look at the samples you're using for this logistic regression problem you formed, let's say we're trying to resolve it for site N, what you want is that for each site J that's not N, it should have lower bounded variance given the other spins in that sample, as well as maybe the previous samples if you're working from dynamics. So it turns out to be the case that for nice dynamics, like these nice Markov chains I mentioned, you can do so by kind of directly writing out the likelihood ratio of the spin at site J. If you kind of pretend that I didn't know the spin at site J and I looked at all the subsequent updates along the path, at least between the samples, and then I asked what was the probability that xj was +1 or -1. So it turns out that the likelihood ratio won't be bounded with probability 1, but we'll still be able to find a constant probability event over the law of these updates of the trajectory where that is the case. And so you can get the analytical tools you need to establish logistic regression succeeds. For the high temperature IID samples case, these C operator norm bounds will actually just directly imply a good enough variance lower bound with constant probability for any site J that's not N. And so again, this will be enough to kind of establish that logistic regression works once you also have this uniform convergence. And so in the particular case of the SK model, you need now covariance bounds because we know that the interactions lie in like the L2 ball, for instance. So these operator norm bounds are really just like kind of the spectral operator norm bounds. And for SK, this is very recently established in some recent work by a couple of different groups. And to go kind of to these Gaussian external field case, you need to do a bit more because now the measure no longer has mean zero. So you kind of need to look at different matrices and kind of use some other spin glass techniques of Talleyrand, but you can still kind of get it to work with enough technical effort. So just to conclude, our main result is that this standard approach for the IID setting, logistic regression, it'll succeed in recovering more general Ising models and under more general observation models than previously known. And in particular, there's no algorithmic modification necessary. So one question that's interesting is for our dynamical results, we require to be able to see which sites are trying to update at each time, regardless of whether their spin value actually flips or not. So one thing would be interesting is whether it's still possible to learn from dynamics sufficiently when the subset of nodes that updates at each time isn't actually observed. You only see which sites change. Another question is, our results for the dynamical setting, they still relied on this L1 bounded width. It'd be interesting to see whether this can be relaxed just like it was for the IID setting for these high temperature Ising models with these covariance bounds. The last thing is kind of those high temperature Ising bounds, they relied on these kind of covariance bounds that are in principle weaker than things like fast mixing. So one potential place where there could actually be a separation where something like these covariance bounds hold, but rapid mixing is provably false would be something like these kind of high temperature p-spin models once you kind of go beyond the Ising setting. So it'd be interesting to understand whether there are settings where these kind of weaker reductions that we use to covariances are kind of necessary to establish efficient learnability.